Being at CppCon has been amazing because you can directly speak with the experts. I've had conversations with Bjarne Strusepp, with Sean Parent, and they're all very friendly and accessible and willing to give their opinions or advice on C++.
My name's Christopher Fretz. Chris is what I usually more typically go by. Yeah, we're going to talk about designing a slimmer vector of variance today. I work in Bloomberg, as the slide would suggest. I work in Ticker Plant Developer Experience. So obligatory comment about if anyone is looking for a job. If you like what you see, come talk to me afterwards. But cool. So let's go ahead and get into it. So starting out with kind of an overview for the talk here. So this talk details my experience in creating a novel solution to an observed problem with memory usage of std vector, std variant. And so this talk starts by kind of discussing the motivated use case, like why did I take the time to do this? And then kind of considers several different candidate designs, incrementally refining and working towards kind of an ultimate design. And then kind of presents interesting implications of the approach, benchmarks, and just kind of talks about lessons learned from going through this process. I implemented, this was motivated by an actual like production use case, but I mostly implemented the data structure for the fun of it. It's coming out of C++ now last year. I remember I was like, I gotta learn C++ 20, I gotta find some project. So this ended up being a very fun one to work on. The final presented design in this presentation is kind of a simplified version of the actual data structure, but it should illustrate the point. What are we actually talking about here? Why do I care about the memory usage on variant? Heterogeneous containers, which is to say like containers that can hold many different types simultaneously, is an extremely natural way to represent data across many different paradigms. The problem here is that depending on the way that your types are structured, and specifically if you have a few types that are like way bigger than any of the rest of the types, std vector, std variant can result in like comically bad memory utilization, like shockingly bad. This is kind of where this started here. So it looks really pretty for slide examples and stuff like that, but it can lead to very significant bloat in real world code. The original motivating use case here was modeling a time series of market data events as a vector of variance. And one of the types in the variant happened to be like 10 times larger than the rest. This is where you start to run into problems. And I was going to say, the person who actually originally ran into this use case is in this room. Thank you very much, Ariel. But it was kind of a fun collaboration. But cool, awesome. So that's why we're talking about this. Just as kind of like a starting out little bit of trivia here, do we have anyone that wants to guess how much memory actually gets used by this vector? So we have this combo type thing here, which is just a variant of bool, int, double string, and this big data thing. Big data is just a 5K character buffer. And inside the vector itself, we just pass a bool, an int, a double, and a string. So there is no big data used here. But does anybody want to guess how much memory actually goes into the heap off of this thing? Yes?
20,000 bytes.
That's about correct, yeah. So we got a correct suggestion from the audience of about 20 kilobytes for this particular data structure, which is the problem itself. To kind of get at why this is the case, so we're going to be looking at a bunch of these kind of informal diagrams that I've put together. Below the dotted line here is the stack. So we can see if we take the previous example here of our vector of combo type, this little box down here is the actual vector class sitting on the stack. We got its size, capacity, and data. And then this up here is the contiguous storage array that actually goes into the heap. What we can see here is that even though we're storing essentially trivial data in these variants, every single one of them is over 5,000 bytes wide. What we end up getting here is just ludicrously bad usage of the memory that we've actually allocated. Why is this the case? So the kind of the core of the issue here is that standard variant always stores the wrap type inside of the class. I think it's one of the strengths of variant, generally speaking. It gives it very good performance characteristics, very good, no allocation characteristics. But the problem is that in this particular case here, it means that it must always pessimistically be at least as large as the largest t. And so if one of your t's is 95% bigger than everything else, you're going to end up using that all the time. And so standard vector assumes that all of its elements are the same size. Variant can't allocate. And so this brings us to our failure state, requiring 20 kilobytes to store a single bool int, double, and string. And so if we assume that a bool is 1 byte, an int is 4 byte, double is 8, a string is 24, which is pretty typical for your x86 64 architecture. The minimum conceivable memory usage, I'm not saying this is actually realistically possible, but the minimum conceivable usage is 37 bytes, which means that we have a bloat factor here of 540x. And so this may seem kind of contrived here. I could have said 10K and then we'd be talking about 40 kilobytes instead of 20. So it may seem kind of contrived, but this is actually really not so far from the actual use case, the actual problem that we ran into. Once you get into a non-trivial code base, you've got lots of type aliases, not everybody's super familiar with all the types, it's very easy to accidentally construct these circumstances. And so may seem a little bit crazy, but it's actually really not that hard to do. And so, why is vector variant so wasteful here? Vector and variant are generically composable containers that don't cooperate with each other, they don't know about each other. And I think that this is generally a strength of the STL. The fact that you can just compose these things together and they work is amazing. But in this particular case here, given the characteristics of them independently, this is kind of the necessary outcome. Variant can't allocate, and if you assume that all the data is the same size and you have to store it inside of the object, this is kind of necessarily the outcome. And so it begs the question of, can we do better? The answer kind of has to be yes, because we're talking about a bloat of 540x. So there must be some way for us to do better. And so let's try to do that. So starting off here with our first candidate design. So say that we relax the limitation that standard variant can't allocate. Where would that actually get us? And so that would might get us to a design that looks a bit more like this. So again, below the dotted line is the stack, above is the heap. Nothing's changed about the vector, but up top here you can see that now our variant instances, every single time it holds a type index and a pointer to somewhere else off in the heap. And so we now, for the actual type storage itself, we only use what we need because we're directly allocating the types individually. And so this does a lot better with memory usage. This only uses 101 bytes. So compared to our theoretical minimum, we're down to just 2.75x. So this is a whole lot better in terms of memory usage. The problem, though, is that now every single pushback into this vector is now going to allocate because the variant, it's now unconditional allocation. So every single time you push something into this vector, you're going to take a heap allocation. And we've completely changed the performance characteristics of the data structure. The memory ceiling is way, way lower. But if we're going to have to allocate every single time, this is not going to be a performant data structure. And there's also problems of heap fragmentation, all sorts of things that come into this. And so again, can we do better? There's got to be some way for us to do better here. And so, interestingly enough, so the performance overhead for allocating for every variant, if you're going to the global allocator, it's massively expensive. So the interesting thing, so this is not the direction that this talk goes into, but one thing that I've been thinking about recently is that you might also be able to try to mitigate the approach of just allocating for every variant using a std PMR memory pool. And so the idea here, it's actually really cool because we actually just have memory pools in the standard at this point now. They came in with C++17. And so the idea with this one here would be to have your allocator kind of allocate large chunks of memory as you go. Now, the problem is that you start, if you're allocating large chunks of memory, again, is that going to over allocate? There's interesting concerns there. But you can at least try to mitigate the overhead of trying to go to the global allocator every single time. Even in this case here, if your data is trivial, which it was in our case, it's mostly built-in types that we were trying to store, the pointers themselves in this model can actually still become a source of significant memory bloat, just because, if you're trying to store a bool, the pointer that you have to use is larger than the bool itself. So you can still get significant memory bloat just from the way you have to represent it. And you also are going to be taking kind of chunked allocations, and until you fill up that whole allocation, you may waste memory. But this is kind of a potentially interesting direction that we could go. So this is not the direction that this talk goes in, but it's something I was thinking about as an alternative. Instead of taking the approach here of allocating inside of the variant, let's try to keep the original kind of characteristics of the data structure here. If we instead were willing to write our own vector class that was actually aware of the fact that it's storing multiple different types, what might that look like? And might that get us to something that might actually do a little bit better here? And so this brings us to our next candidate design here. So down on the stack here, we now have a VV vector. The layout of it is exactly the same, but the idea is we now have a custom vector type. And up in the heap, we now only store the types that we actually want to use. And so like, this looks great. We're at 37 bytes. That was our theoretical minimum. That was easy. And people say that C++ is hard. Thank you very much, ladies and gentlemen. The talk was a little bit shorter than I expected, but it's, no. Obviously, I'm being facetious here. So this is not going to work for all sorts of reasons. So some problems with candidate design number 2, which is how do we actually get things back out of this vector? Because the problem is that like we no longer know that all of the types are the same thing. And so say that you want to access index 1. Where is index 1? Like we don't know. Like vector would just compute off the fact that all of its elements are the same size. And so we have to know how we actually get to these things. But then additionally, how do we know what type it is? Like, you might have a whole bunch of different types that are all the same size. But if you don't know what to cast it back to when you give it to the user, you're not going to get good semantics. And so we also have to know what type everything is in this vector. And so we're going to have to do a little bit more work here, which brings us to candidate design number 3. So it's the same as design number 2, but let's try to actually add like some additional storage to keep track of the types and offsets. We're going to have to be careful with that to make sure that that additional metadata does not itself become a significant memory overhead. But let's try to take a look at what this might look like. We can use integers to store both the offsets and the types. And so the idea here basically is that the offset is just the number of bytes from the base of the storage array. It's very basic. The type can be stored as the index in the variance type list. And so what I mean by this essentially is that in the example that we've been talking about of bool int, double stood string, 0 for bool, 1 for int, it's just the index in the type list itself. And so that gets us something that looks more like this. So our vector on the stack here is a little bit bigger. I'm not terribly concerned about the stack usage in this case here because it's constant. It's still not really that big. But we do have 2 additional pointers here. So the primary storage array itself still looks the same over here. We've still got that 37 bytes. But we now have 2 additional arrays over here. So we now have an offset storage and we have a type storage. And so if you want to access index 1, what you're going to have to do that is you're first going to have to go into the offset storage. You're going to load offset 1. That lets you know where the actual type itself begins. And then you're going to go into the type storage and find out this thing's an int. So I now know what type to cast it to when I give it to the user. And I also know it's 4 bytes wide on the platform that we're on. So this gives us basically all of the information that we actually need here. And so this design uses 69 bytes. So we're now actually both more memory efficient than design number 1, and we're also significantly faster at the same time. Question? So you are slides ahead. We're going to get there. Actually, I won't repeat the question because it's a spoiler. But that is a very good question and it will come up. But yeah, so this is better memory performance and better overall performance because we're no longer allocating. We can still have the amortized cost the amortized growth that we expect out of vector. And so yeah, we can now correctly discern between types and offsets. And so like we're good to go, right? Well, we can start writing tests and figure out if we're good to go. And this is perhaps a little bit more contrived outside of Bloomberg, but just for the fun of it, let's try running it on Solaris and see what happens. And so let's take this example program here. So we have our VV vector type up here, so it's parameterized by all the different types we're trying to store. We just put the same values in here, and then we just iterate over this thing, visit each one, and just try to print it out. And so since we're using standard cout, we should expect to see like 0, 1, 2.0, and 3 is what we should expect to see come out of this program. And if we try to run it, That's not what we get. Okay, so we print the 0 and then we core dump and die on a bus error. So that's awesome. There's something terribly wrong going on here, unfortunately. And so what is it? Well, there was a spoiler a bit ago. The issue here comes down to memory alignment. So this is not something that we typically really have to worry about in C++ for the most part, unless you're manually laying out your own memory like this particular data structure is. Like the compiler and the language together actually kind of work to try to abstract this away from you. And so for the most part, like if you just write your types and you just declare them like you normally would, the compiler knows what needs to happen here and it just injects this stuff for you. But since we're writing this ourselves, we don't actually have this. We're laying it out ourselves and we've done the wrong thing. The reason that I chose the example of going with Solaris is because, so the issue here at the end of the day is that we bus error when we hit the int because the int's not properly aligned. It is UB to do this, but what actually happens is platform specific. And so if you do this on Linux, it will probably actually work, or appear to work at the very least. The CPU will actually fix it up for you at runtime and just issue 2 different loads and just make it work. It'll run slower and the read won't be atomic. Like there's nasty things that come out of it. But the reason I wanted to run it on Solaris is because Solaris will actually trap and die on this sort of thing. That being said, if you instrument your program with UB sanitizer, that will also do the same thing. So if you want to make sure that your code is alignment safe, you just use UB san and it'll scream at you when you do the wrong thing. So let's take a concrete example here. So this is kind of what I was talking about before here. So if you kind of like, I don't know, naively ask like, your average CS 101 person or something like, how many bytes does this struct use? Well, we might assume it's 1 for the bool, 2 for the short, and 8 for the long. So it's 11 bytes in total, right? And yet, if we actually ask the compiler, what is the size of this struct, we're gonna get back 16. And so like, what is going on here? Because we did not declare 16 bytes of storage in this array, in this struct. So what we actually end up finding out here if we try to zoom in. So this is kind of a layout of the structure that we just declared. So over here we have the offset of the Boolean, we then have the short, and we then have just 4 wasted bytes over here, and we've got 1 wasted byte here. And so what we end up finding out is that like individual types actually have have requirements from the hardware in terms of the addresses that they're allowed to exist at. And so in the case of bools are pretty flexible. They can go more or less anywhere. But a short has a 16-bit alignment requirement. And so the problem is that if we just put it right over here, that wouldn't actually work. The type would not be aligned correctly. And if we move on to the next slide, we can see we have 4 bytes of padding at the end of this slide. If we move on to the next one, we can now see that that's the next 8 bytes of the long itself. And so the different types actually have requirements in how they're stored. And so the long has to be 64-bit aligned, the short has to be 16-bit aligned. And so when you actually do the math for this, you have to add these padding bytes so that things wind up in the right spot. And the alignment requirement is something that is very architecture specific. It will depend on the machine that you're using, but the tool chain always knows this and will just do the right thing by default. And so if we go back to our example that we were putting together, the real problem here comes down to the fact that, this bool is 1 byte. The bool is definitely properly aligned, so that prints out correctly. But once we actually go to print the int, we end up trapping because the int is now at offset 1, which is not well aligned for basically anything. And so what we really need to do here, this is what we currently have. What we really need to do here is we need to shift that int down by 3 bytes so that it's actually properly aligned. And what we end up finding out, so actually I had some explanation here. Misaligned accesses are always UB. x86 handles this automatically. Spark traps with an exception. And undefined behavior sanitizer. So I got a bit ahead of my slides there. What we end up discovering here is basically just the whole rest of this structure ends up being well aligned automatically once we add those 3 padding bytes. And so moving on to candidate design number 4, let's do the same thing as design number 3, but let's ensure that this time our data is actually properly aligned so that we can actually use this data structure without invoking undefined behavior. And so C++ actually has features here that can help us do this. I don't actually know when a line of was added. That might have been an 11 thing, I'm not sure. But align of is a keyword that we can use. You can just pass any type into it, and the compiler will just tell you what is the native alignment requirement of that type. And so if you call this with int on x86, 64, you'll get 4. We also have align as. And so you can't use align as to lower the alignment requirements of a type, but you could use align as to say, I want to over-align this type for some specific reason. And so you can use that to, like an example of where you might use that is if you're doing like in-place construction inside of the data structure or something, and you have like a character buffer or something, and you know that the thing that's going to go into that character buffer is going to be another type, you could declare that with an align as specifier to ensure that it needs to be properly aligned. Question? I think it can take either, if I'm not mistaken. I think you can give it a specific alignment, so you could say align as align of t. I think that does work, but you can also just say align as t. It'll take either. But good question. So yeah, the question was, does align as take what align of returns? And I think it will, but it can also be used just with a direct type. And then this one, actually, a lot of people don't know about. I know this one came out in C++ 17. You can actually do aligned allocations in the standard now, too. So you can actually tell the global allocator, when you go get me memory from the heap, I need the pointer that you return to me to be, 16 byte aligned, or, well, it usually is by default, but like 64 byte aligned or something like that. So there's actually a lot of really useful helpers in the standard that can help us do this at this point. And so if we end up kind of redoing this design here and trying to actually correct for this, this is what we wind up with here. So you can see that we now have these 3 padding bytes for the bool. So the bool is now obligated to take up 4 bytes in our data structure. And then everything else is just properly aligned at that point. If you swap the ordering here, then you'd end up with some different alignment requirements. But with the way this is laid out right now, it does actually do the right thing. And so this ends up wasting another 3 bytes to get us to 40 bytes, but it does actually work. So that's kind of an upside. So yeah, we finally have something that actually works portably and reliably, which is really nice. And at this point now, our design requires 72 bytes to represent this. It's slightly worse than design number 3, obviously, but it's, it actually works. And it's also a far cry from the original 20 kilobytes. So this, I think, gets us in a pretty good spot to start with. But it still begs the question of, can we do better? Because I think we probably can. So candidate design number 5. So currently, at this point now, we have a data structure that works. It's portable. It does the right thing. Uses way less memory than what we started with. But currently, still nearly half of the actual heap memory that we're allocating for this data structure just goes into metadata. It just goes into the offset and the type storage, which is pretty unfortunate because it's almost clear half of our memory usage. So we have to be able to do better than that. So a couple observations here. So first off, for any specific instantiation of this vector class, there will always be a static number of types that our vector is parameterized by. From one specialization to another, it's not going to be the same set of types. It might not be the same number of types. But for any specific specialization of this, the number of types is never going to change by definition. And so the other thing is that it's unlikely that the vector will ever really use more than a handful of types. Might you have a vector that uses 4 types? Yeah, probably. 8 types? Yeah, sure. 16 is getting less common. 64 types, who would do that? You would have to be a crazy person. So it's, who knows? But there's probably some use case for it. And the data structure should be able to handle it. But the average case here is that we're going to have just a handful of types. And so if we know how many types we're going to have to store, and we know statically that it's never going to change, we can actually compute the minimum number of bits that are actually required to uniquely discern between the types. We can then store this type info in a bitmap, and that will radically decrease the additional storage requirements that we need for this. So that's the first observation here. The next observation is that if we can put an upper bound on the size of the vector, we can do the same kind of thing with the offset storage. We can actually compute the smallest integer type that will be able to represent the maximum offset. So the actual library that I've put together for this handles both static vectors and dynamic vectors. And so in the static vector case, it's trivially easy. You just know how much space you're going to have because it's very much like in-place vector where the user just has to tell you how big your vector is going to be. But it needn't actually be a hard limit. If we have the ability to kind of swap out or rebuild our index storage at runtime, we can actually dynamically select the smallest representation that will suffice. And Yeah, we'll get into the implementation of this, but this does actually end up working fairly well. And so candidate design number 5 here. So we're going to replace the current type storage with a bitmap. We're going to have the bitmap store the types using the minimum bits possible. We're going to replace the current offset storage with a virtual interface that will allow us to transparently rebuild and swap out the offset storage with the minimum usable type at runtime. And combining both of these approaches should get us significantly closer to our theoretical minimum. And so we wind up with something that looks kind of like this. So if we look at the types here, so the example that I've been using of bool int double string only has 4 types. And so we can actually represent this with only 2 bits each. And so we only have 4 things in our vector right now. So we can actually store all of the type storage in a single byte, which is actually pretty awesome. And just as a little aside, like writing a bitmap like this in C++ is actually quite a lot of fun. You can have a good time with it. But then the offset storage here at the current moment, the maximum offset that we need to represent here, it's actually not even 40. I guess right now it would be like 26 or something. But we only have 40 bytes that are in this array right now. And so we know for a fact we can represent everything with a single byte for each offset because a single byte can represent up to 255. And so right now, we only need 4 bytes to actually store all of the offset information. Where this gets kind of interesting is that obviously, the user that's using this vector might keep pushing more and more things into this. And eventually, we will trip beyond that limit of 255. And so what will actually happen in my code today is that when we go beyond that final boundary, or when it computes that it's going to go beyond that final boundary, that's the point where it will actually go and rebuild all of this offset storage. It'll move next to 16-bit integers, 32-bit integers. It'll just kind of slowly expand as it needs to. And the thing that's kind of interesting here, like what I really wanted to solve was this case where we have like a relatively tight, like relatively small vector, making sure that the offset storage is not a significant portion of the total memory in that case. But as the vector gets larger and larger, like the offset and the type storage are going to be smaller and smaller portions of the total memory usage as well. So this does actually tend to scale fairly well in my experience so far. It does, of course, mean that if you happen to be the unlucky person that pushes in the thing that pushes us over 255, you're going to get a little bit of a stutter in that push because it's going to have to spend time reallocating this. But it does actually work pretty well in practice. And so for candidate design number 5, this optimization brings us to a grand total of 45 bytes. For the full representation. Our theoretical minimum was 37 bytes, so this is actually pretty good. It's only about a 20% overhead versus the theoretical minimum. So I was pretty excited about this. Can we still do better at this point? Perhaps. There are some things we could probably do. I mentioned if we can handle the dynamic case, a static vector implementation should be a trivial extension. It's literally just cutting things out and just making it simpler. Static vector can also store the contents in situ inside of the class, which means it would work exactly like in-place vector is meant to. One other thing that's kind of interesting here, I don't know if anybody's ever had to write a type in C++ that is conditionally copyable or conditionally movable. Back before C++20, this used to be incredibly painful. You had to actually do like conditional inheritance because you couldn't just sphenate out a special member function, like it was just not legal. But starting in C++20, you can get rid of that conditional inheritance. Like you can just actually put a requires clause on a copy or move constructor now. And so like this type can just say, in its copy constructor, like requires stood copyable of like all the t's that it stores. And so you can just, essentially just requires out special lifetime functions now, which is really cool. There's obviously very natural extensions for constexpr here. Nowadays, you have like constexpr allocation these days, so you might actually be able to get this entire data structure to be constexpr. But there's obviously very natural extensions here in the static case. Another additional idea here, if you care about like absolute minimum memory usage and you're willing to like do some things that have negative consequences, we could also store trivially copyable types contiguously without alignment. What we could do here, you can't do this with actual objects because like you can't call a copy constructor at a misaligned address. But if you are just working with trivial types, you can actually just store them with no alignment at all and then just bitblit them to like an aligned address before you hand it back to the user. So there are tricks that you can do there. That's, I think, probably to the point where this is like diminishing returns, and I don't know that this one is really worth doing, but you could conceivably do this. Yes?
Sometimes you need to return a reference to the internal.
So that is a very good point, and that will end up coming up. So the comment here is that if you take this kind of approach of storing things misaligned and you want to hand it back to line to the user, you can't give them a reference in that case. Because if you're aligning through the stack, like that frame is going to be dead by the time you return back to the user. So this does that. When I was talking about this has negative consequences, that's the sort of thing that I was talking about. You could still make this work with like visitation. Like, depending on how you implement that, you can align it through the stack and then pass into the visitor as a reference there. But then it still comes down to a question of how do you propagate that back to the in-place storage. So there are still consequences here. But yeah, that is something you can do if the memory usage is the only thing you care about. But cool. So let's talk about the implications of this design. We now have a candidate design here for a data structure that like radically reduces the memory footprint from our original example while retaining essentially the same functionality. And this works very nicely to solve our original problem of memory usage. But do these changes have any implications for the data structure's wider API? And the answer is that they do, unfortunately. So let's talk about the challenges of mixed type storage here. So the original idea with this data structure when I was putting this together is that I wanted to, insofar as I possibly could, model this as a drop-in replacement for standard vector. Where you start running into interesting problems, though, is that a lot of member functions in standard vector silently assume that all of its elements are the same size. So, for instance, what does capacity mean for this data structure? Because, well, like, literally, what does it mean? Like, what should I say? Like, capacity of what? Like, what type do you mean? And so that is kind of a difficult problem. What does reserve mean for this data structure? Like, if you say, I want to reserve 10, of what? Like, it's not clear what you actually want to reserve. And so what about resize? Like, there are multiple, like, there's kind of a cascading problem here in terms of the API assuming that all of its types are the same size. And so all of these functions that operate on like the number of logical elements becomes kind of problematic for a data structure like this. Because normally vector can just directly infer the number of bytes that like means, but we can't do this. And so this is the approach that I've taken so far. So you can see here for vector here, I have a couple different overloads. I have this reserve bytes function, which just tell me what you want and we'll do it. We'll make sure we have at least 64 bytes. But we do also have reserve functions here that can be, for instance, like explicitly parameterized in terms of what I mean. So in this particular case here, I mean that I want room for 16 strings. And so it will actually then go and do the work as you meant it there. In the case of resize, if you pass a default value, I can infer what type you mean off of the default value, and so you don't have to explicitly say what you want. If you don't pass a default value, then you also would have to say resize to the string. But so you can take that kind of approach. We can do the same for capacity. I also have a capacity bytes function here. And so the idea is to try to model it as closely as we can. But this is just kind of like an inherent conflict between what we're trying to accomplish here versus the API that we're trying to model. And so this was, kind of an interesting problem space. More implications of design. So we have semantic challenges for the number of elements function, like capacity, like I said. There is also significant complexity that ends up getting added for functions like insert and erase. I was not originally sure if I would have enough time to go over this section, and I wish I'd put the slides in because I actually do. But it ends up being really challenging because say that you want to insert a bool onto the front of your vector. Like that's the worst possible case because it's going to screw up the alignment for the entire data structure. And so the problem is that if you want to figure out, do I have enough space to complete this insert? It's usually like for vector, if you do an insert, it's just, do I have, size of value type? Do I have that many bytes left? In this particular case, it's not even that because size of bool is 1, but putting a bool in there can have cascading alignment implications. And so what you actually have to do to actually complete something like this, to start the insert in the very beginning, you have to actually walk across the vector to figure out what is going to be the cascading alignment impact of this. You can then compute, how much space do I need, including the realignment that I'm going to have to do. And then you have to walk backwards over the vector and move things forward to make space for the thing that you're actually creating. So this ends up being kind of surprisingly challenging to implement. There's also kind of a really interesting edge case that you can wind up in here, where say that you had a bool at the front of the vector and it's all strings from that point forward. String is gonna need an alignment of 8 bytes, which means that you're gonna end up moving that string by less than the size of the string itself, which gets kind of super weird because you have to start worrying about overlapping pointers during these move operations. So you start running into all sorts of weird edge cases for insert and erase. They are implementable. My data structure does do it. But there's some surprising challenges here. Are there any other implications? And unfortunately, the answer is yes. We're now going to talk about what was alluded to previously, which I'm calling the woes of the subscript operator, unfortunately. While the design that I've presented here thus far minimizes memory usage very nicely, it has unfortunate implications for the subscript operator. So consider the following code here. So this is just using standard variant. There's no special types here. This is none of my stuff. So we again have our combo type of bool int double string. We declare a vector that has the same values that we've been using for this whole talk so far. We then just try to assign a new value to the fourth element, the third index. And hopefully this is not surprising to anyone. After this assignment completes, we then do std_get to get it back out of the variant, and we get the value that we updated it to. Like, this is hopefully not surprising code. So how does the assignment inside of main actually work? And so I mean this like vec sub 3 equals 1 plus 2. What actually happens on that line? So the subscript operator of standard vector returns an L value reference to the requested index. So it returns an L value reference of type std variant and whatever the types are inside of it. We are then assigning to an L value reference of variant. And so the assignment operator of std variant is called, and it does some template magic internally to ultimately decide what is the runtime type of this variant, what am I assigning from, like what do I actually need to do here. And so this ultimately ends up calling the assignment operator of std string. And so then the assignment operator of std string inside of the variant receives the string literal, changes its value, and then causes the print statement to see the new value. So this is how it works in a standard workflow. Again, hopefully this is review and not surprising. So this kind of begs the question, what happens if we try to do the same thing with our vector? So this is now my vector here, VV vector, and we have the exact same code. And you will find that this code builds, it runs, it doesn't throw, and the value does not update, which is terribly unfortunate. And so why does this happen? Like, this was genuinely upsetting to me. Like, I wish I could at least make this code fail to compile, but I've not been able to come up with a way to do that thus far. So what's going on here? The assignment runs fine. There's no exception that's thrown. There's no error that happens at runtime, and yet the value just silently doesn't update. And so, like, what gives? So the issue here lies in the first bullet point of our assignment explanation. The subscript operator of std vector returns an L value reference to standard variant. The problem here is that like vector is storing a variant, and so it can return a reference to it. But like our data structure isn't. That's actually the whole point, that we're not storing a variant. And so the problem is that I have no reference to give. And so if you call the subscript operator, like the subscript operator has to return a single concrete type. It can't return, like, you know, the compiler doesn't know off of some runtime index what type it's actually going to be. And so the subscript operator has to return one thing. And returning variant means that it can represent everything it might need to store. And it also means that we have, you know, out of the box compatibility with like standard visit and stuff like that. But the problem is that because of this, I have to actually construct that variant at return time. The question. Mm-hmm. So that doesn't actually solve the problem either. Like the problem is that the issue is that the variant doesn't exist until the time you ask for it. And so if I wanted to do something like that, I would still need somewhere for the variant to go. Like I can't store it on the stack because I'm about to return. Well, true, but I mean, True. The problem is that if I actually just wrote that code, what you would actually get would be a dangling reference. Like I would be returning a reference to a local, which will just dangle immediately. So like what I could conceivably do if I really wanted to get creative here, I could actually construct like a default constructed like variant instance inside of my class, like assign through that and return a reference to that. I don't want to do that. I could also maybe do like a one-time heap allocation or something to create a variant to kind of pass through and then return a reference to that. But short of kind of getting very creative like that sort of thing, I don't know that there's really a clean solution to this. And I had a couple other questions here.
With the vector variants, you can change the type, I think, right? It would compile and work.
Mm-hmm.
If you did that, say you did get this to work, I don't know if you'd want to put it in your API because I could change the type and then it would mess everything. You'd have to like move everything.
Correct. Yeah, the way that my library actually works with this is that I have a dot replace function. Like replace ends up just being a special case of insert, essentially. But that is a good point. So the thing that's interesting here again is that like I am never storing variants inside of the actual contiguous storage in the vector, and so I would never have to worry about them screwing up my bookkeeping by like assigning into something I don't have space for because I'm not storing it there. But the fact that I'm not storing it there is what makes this problem so like intractable, unfortunately. I have another question.
What I was just going to say, when you were suggesting to make it a cons, the return type cons, that wouldn't solve the problem. Would it make it where you said you wanted to get this where it would fail if you tried that?
Mm-hmm.
With const, you do that.
So if I was able to return a const reference, that would get the assignment to fail. That would definitely work. The main problem is that again, so like the way that this logic works currently is that when the user asks for this thing, like I construct a temporary variant on the stack essentially. Like I make it on the fly and return it back to them. If I just turned that into const ref, like it would compile and I would then give back a dangling reference. So like that's part of the problem there is that I can't return a stack variable like that. And so that's why I was saying before, like I need somewhere to put this thing. So like maybe I could just declare a variant inside of my class and return that, or like make a one-time allocation of construction time and put this thing in the heap. But I'm afraid that like I think it's better to be honest about the limitations here instead of trying to get like overly clever about how we do that. Another question.
Usually the solution is to return a proxy type, which has an operator
So that is a very good point, and that is something that I considered. The problem is, and I thought I had a slide for this. Maybe I don't. I don't know. Yeah, I thought I had a slide for this. So the reason that I didn't do that, because I did consider doing it, the reason I didn't do that is because I think that's how vector bool works. And vector bool is famous for being well loved in the C++ community for this reason. And so like that would work.
The problem is that it claims to be a specialization of the vector. It's not.
That's true. Yeah, I could just document this as different semantics. So the comment for the YouTube audience, the comment here is that we could have this return a proxy type. So the idea there essentially is that you create a new type whose sole job in life is to overload the assignment operator. And what you could do is when we return that type, like it caches a reference or a pointer back to the vector that it was constructed off of. It knows what index it refers to. And then when you call through its assignment operator, it just does the insert for you essentially and does the right thing. We could do that. And the way that it would be typically done there is that you would then have an implicit conversion operator so that the type actually implicitly converts to the underlying type so that if somebody just said std variant whatever equals subscript, it would just do the decay and it would work automatically. The reason that I still don't like that is because like the moment that you declare auto or you pass it into a template function, like it's not going to decay. You're just actually going to leak the proxy object into the program. So that is a possible way forward, but that's not what I've chosen to do here. The other thing that did occur to me is that if I was willing to implement my own variant type, I could actually have the variant work as its own proxy object, but I decided not to go in that direction. Any other questions from anybody on this? It's a very good point though, and it's a really interesting design space, I think. But cool, awesome. So yeah, this is extremely unfortunate. Inevitable outcome of not actually storing variants inside of the vector. Oh, I did, okay. Could theoretically work around this with returning a proxy class, but this seems like an anti-pattern. So to work around this at the current moment, we need some new APIs. So the approach that I've taken here to start with for now is that like I just have like .get and .visit and stuff like that implemented as member functions. And so if you call .get, you can give it a concrete type, and then this actually will return an L value reference to int because I actually am storing one of those. And so this allows in-place mutation, same with string. And with visit, you can still do this without knowing what the type is because that auto ref, like this is actually a real L value reference. I'm again exporting out the actual actual thing that I'm storing. And so you can mutate through visit, you can mutate through get, and it works the way you expect. But again, the thing that's really unfortunate to me is that I can't make the subscript operator assignment fail. I actually thought about even just removing the subscript operator, but like, is it really a vector if it doesn't have a subscript operator? But yeah, so this is the approach that I've taken for the time being. So yeah, the .get and .visit APIs model their STL equivalents and allow for in-place mutation. The subscript operator does still work as expected for read-only interactions, which is why I've kept it around. Like this sort of thing does, sort of what you expect for some definition there. The problem is that, again, if you assign to val, you're assigning into a temporary variant, so it might still not really do what you expect. But you can at least get read-only interaction with std visit the way you would expect. So we have semantic challenges for the number of elements functions. We have complexity of implementation for functions like insert and erase. Not storing actual variants leads to difficulties for the subscript operator. And I think that these are most of the problematic implications. It is really interesting, though, to see how like a seemingly simple modification of the implementation of the data structure really can bubble up to the public API in this way and kind of really constrain what you can do. But I was going to say it's not a real C++ talk if we don't get into benchmarks, so I do have to do at least something here. So this is just going off of my reference implementation, just running on my work laptop here. This is, what are we looking at here? So the text is kind of small. I apologize about that. But the idea for this one here is that we're trying to benchmark just what is the overhead to access like an object through the subscript operator. I have a static vector implementation here, a dynamic vector, and then standard vector. And so what you can see here is that when we're accessing a Boolean, an integer, or a float, if we're going through the subscript operator, we're going to be creating a temporary variant, which means that we're going to be copying out. And so when you're working with trivial types, it doesn't really make that much of a difference. Like the static vector case here appears to be exactly equivalent to vector. I'm not sure that I really believe that. I think that GCC might be optimizing a little bit too hard. But if you look at the std string case, we actually do see the overhead from having to do the additional copy. So that's more or less what we would expect. But in this case, either way, if you look at the y-axis here, we're measuring in time in nanoseconds. So like, it's not a huge overhead that we're getting from this approach for trivially copyable types. This next one here is looking at what is the timing for pushback and popback. And so the idea here is just that we just try to push into the vector and just kind of immediately pop back out of it. So again, we have the timing for Boolean, integer, and float, and then string on the far right. I'm not really 100% sure why my dynamic vector is so much slower than std vector in this case. This might come down to the fact that we have to take the hit through the virtual table for the index storage. We do have some kind of meaningful overhead. But again, it's order of like 20% or something overhead. And then standard get timing, this is just again calling like, std get versus .get on my thing here. One thing that I really don't understand, so this is working with libc++ because I'm compiling this through Apple Clang. For some reason, this is literally just raw std get of a string out of a vector. I do not understand why vector is doing so badly on the far right. I don't really know where that comes from. But yeah, this is what we're seeing overall here, which is that the dynamic vector continues to have overhead, probably from that virtual table indirection. But the static vector and std vector are kind of more or less parity in terms of performance. But this is all the actual runtime performance. But at the end of the day, the actual point of what we're trying to do here is to lower memory usage. And so what do we actually see on that front? So this one here is, this is using the same definition of the vector that we've been using the whole time. So it's been bool int double string. And so this is what you see if you only pass integers into the vector. And so this is with 1,000 pushes, 11,000 pushes, 111,000 pushes. I generalized this out to 11 million pushes. It's just that if I put that on the slide, then suddenly you can't see any of the other things. So you'll have to take my word for it that this generalizes out to at least 11 million. What we do find here is that in the case of pushing integers, we actually do save about 60% memory usage, which is pretty cool. This is perhaps not the most realistic use case though, because why do you even have the rest of those types in your vector if you're not going to use them? And so this is pushing random types. So this is taking that, again, that exact same vector of bool int double string, and just, I think, using like the default random engine in C++ to just decide which one of those things you're actually going to push at runtime. And we discover that even when we are actually pushing types randomly, we still save about 40% over standard vector. So we do have meaningful memory performance improvements here. But cool. So wrapping up on the final design here. So we retain a contiguous storage array supported by metadata to track offsets and types. We bitpack all the things that we can. That's how part of the way we save memory. We deal with mixed alignment gracefully. We provide alternative APIs for the subscript operator to work around fundamental design implications. And yeah, the data structure that's presented in this talk is a simplified version of what I actually put together. It leaves many things unhandled, or this talk leaves many things unhandled. We didn't really talk about the difference between static versus dynamically resizing vectors. Doing the dynamic growth for vector is actually pretty interesting because, again, like, not everything that I'm pushing in here is the same size. And so you can sometimes wind up in this weird space of having to do like last minute allocations where you suddenly realize like, oh crap, I don't have enough space. But so dynamically resizing is kind of interesting. Handling types with throwing move constructors. This actually now reminds me, I really want to find out how in-place vector handles that. Because if you're storing the objects inside of your type, types with throwing move constructors can like break your type. So it will actually be kind of interesting to see how in-place vector handles that. Yeah, dynamic growth strategy I mentioned, acceptance safety guarantees, what should happen if something throws in the middle of a pushback or something like that. But yeah, there's kind of a bunch of additional space here. But yeah, this is now actually really the end. So thank you very much everyone for coming. And are there any questions?
Did you do any testing or benchmark testing on the exchanging of or changing data types within a, say, position 1?
I gotcha. So that is
the way that it looks like your metadata is designed.
Mm-hmm.
I could it looks like I could see if you're changing data types on a regular basis, that could become very expensive very quickly. Yeah,
that I think is definitely true. So the question is, did I benchmark the performance of replacing types in a particular index in the vector? The answer is unfortunately not. What it really comes down to is that, so replace for my data structure is a special case of insert because of the fact that like, the type that you're trying to insert or the type that you're trying to replace might be larger than the existing type. It has to handle that whole problem of recomputing alignment and moving everything. And so that's why replace is literally implemented in terms of insert. And my original thinking when I wrote the insert function was like, if you're using vector, probably you're not inserting things in the middle in a performance critical pathway because even vector itself is going to have to move everything and potentially reallocate. It's an interesting thing. I would like to do that, but currently no, I've not put an enormous amount of benchmarking into that. I do expect that it would potentially be expensive. If you are replacing with something that is smaller than the same type, then it should be relatively cheap, but obviously that's not guaranteed. Yeah. Any other questions from anybody?
So great talk.
Thanks.
I was curious if you compared the characteristics of this with like kind of maybe the obvious solution of just like putting some kind of an object buffer in for really large.
Mm-hmm.
You know, so a stood variant of like 1, 2, 3, 4, object buffer 5. You know, and then like, okay, let's allocate because it's relatively infrequent for that one. But the other ones would be like in place in the stood variant.
Well, so I guess, could you maybe give me a little bit more detail on what you mean there? Like,
I don't know how many Bloomberg people we have here, but like if you have a vector of choice types, right? Like the way that works is like they're object buffers of things that are non-trivially copyable, right? And then for the primitive types, they're just there in the union. And so like if you union like int, bool, whatever, like align them and everything, but then like the stuff that you'd have to, that is bigger, you just make sort of a buffer and direction for, and then that's gonna like manage the memory and everything.
I gotcha.
Right, so like that's the big one, and now it's a pointer, and then okay, it's relatively infrequent, so you're gonna allocate for that one, but the other ones get the benefits of stood variant. Right?
And I was gonna say, and I think that maybe this is also getting at the point of like another way that this problem could have been solved is like take that really big type and just put it behind a unique pointer, and then the problem kind of goes away.
Right.
Yeah. So There's definitely a lot of different ways to tackle the problem. It's in this particular case here, I was the thing that really kind of captivated my attention here is the problem of memory usage with vector invariant. So I kind of wanted to try to tackle that problem directly. But let's be clear, there are definitely simpler ways to solve this problem.
I was just gonna say, but it'd be interesting to compare like the simple way, right? How much did you, in the end, get for doing all this work, right? Because it's like you definitely, I learned something. So anyway, thank you.
Definitely. Yeah, thank you very much. Yeah. Any other questions from anybody? Oh.
So you mentioned that you did not see the memory alignment problem on Linux. I'm curious if you know why that was the case.
I actually do. It's Linux itself actually handles this at the CPU level, at least in my understanding. Like with Spark, like the moment that you have a misaligned address, you just get like a bus exception, like it just immediately dies. You actually can have the Solaris Studio compiler inject additional instructions into the program to fix things up if something like that happens. Really what it comes down to is that Linux does this by default. If you try to do a misaligned load, like the CPU will actually fetch both sides of that, like it'll fetch both words around that thing. It'll actually shift everything up and fix it for you. And so it just does this without being asked. So the unfortunate thing about that is that it is slower. You take the hit on 2 reads. The thing that's really nasty is that normally like a 64-bit load on Intel like that would be atomic. If it ends up doing this, it's no longer atomic because it has to issue 2 different reads, and so you can get torn reads and stuff like that. But yeah, that is why it just fixes it. So if you want to actually make sure that your code is alignment safe like this on Linux, you kind of have to use UBSAN. But yeah, definitely.
Great,
thank you.
Would it be acceptable to reorder the elements to have better alignment, like push padding to the end?
That's a very interesting question. Another thing that I think was suggested to me previously was like, could we have like separate storage arrays inside of vector that are dedicated for each type essentially, so that you know that you're never going to have to work with like alignment bytes like that. The main thing that I've been concerned about here is that once you start kind of shuffling things around inside of the vector, then the actual lookup of figuring out where is that thing like starts to not necessarily be constant time. And so the thing, like I wanted to, insofar as I possibly could, try to preserve as many of the performance characteristics from vector as I could. And so I wanted I wanted the computation to figure out where is this thing to be as cheap as physically possible. But it is a really good question. Yeah. Any other questions from anybody? These are good questions. All right, awesome. Well, thank you so much, everybody. This was great. And yeah.